So here we are. Thank you all for being here, and thank you, Crystal, for accepting to give a seminar, webinar, yeah, in our series for young rheologists. So here today with us again is Crystal Owens. Is that correct? Owens. So she's a postdoc at MIT, and today she's going to give a talk about the thixotropy, avalanches, and brittlement and slip, exploring bottlenecks to smooth flow of tomato ketchup. That's great. And I don't know if you know Crystal, but I, of course, as many others in the rheology community, know Crystal because of her work on the Rheology, which was very a very famous work. So please, Crystal, tell us something about yourself before starting dealing with some hard science. Where did you study? Where did you do your undergrad, master's, PhD, and where are you at now? And what's your plans for the future?
Yeah. So I did my undergrad at Duke University.
Hmm.
Actually, originally I'm from Iowa, so right in the center of the US. Then I went to Duke for undergrad. I studied mechanical engineering and math. And then I went to MIT actually for master's and PhD and as a postdoc. Except I did my PhD in mechanical engineering and now I'm a postdoc in the artificial intelligence lab. So I'm doing a little bit different stuff now.
Nice, great. And so I mean, you told me already that you're applying for some faculty positions, so I guess that's the plan, right?
Yeah, that's probably plan A. I feel like I have several backup plans,
Nice. Okay.
including bakeries for 3D printed food and some other ventures, if faculty doesn't work out.
Nice. I guess that's what everybody, we always talk about, I don't know, opening a bakery if research doesn't go well. I think that's one of the many the more common plans B for people in research for some reason. Great. Well, maybe because of rheology of food, that's also one big thing. Um, so please start sharing your presentation. And people, if you do have questions, you heard Crystal, you can ask questions during the presentation. So either write them in the chat. If you're shy, we can read them out for you, or just raise your hand in the Zoom panel, and we're happy to take questions.
Yeah. All right. So I'll get started then. Wait, no, I shared with the wrong settings. Let me share so I can
Okay.
share sound. All right. Um, Yes. So I am actually a postdoc now, but I will be talking about a project that I was doing at the tail end of my PhD. So this was working with John Hart and Gareth McKinley, who I believe everyone in rheology knows. And we were studying specifically tomato ketchup. This is probably one of America's favorite foods, or favorite condiments. And I'll just be giving you an overview of the rheology and how that can impact our daily life. So I'll start with some old commercials for ketchup to give you kind of the idea of the experience.
Their ketchup's coming out a lot slower than ours does.
That's not good manners. Oh, you noticed our Heinz. Here, taste it. Anticipation. Anticipation is making me wait.
Best ketchup I ever tasted.
That's pouring it on a little thick.
Yeah.
Thick, rich Heinz ketchup. The taste.
Yeah, so if you caught it at the end there, they said the taste that's worth the wait. So they made a very big deal about how long it takes ketchup to pour out, as something that I think a lot of people find a little bit annoying. But they're trying to use it as a marketing ploy, as like a signature of how good the ketchup is, like how luxurious it is. There are other aspects of ketchup in the collective consciousness. There's one of my favorite poems is uh, description, shake and shake the ketchup bottle, none'll come and then a lot'll. So this is you try to get ketchup to come out, and then all of us like nothing comes out, and then all of a sudden you get a whole bunch more than you wanted. This is by a witty poet. And then there's an ad. So the video was from an ad from the 1980s. This is an ad actually from 2024 that describes a guy who has spent 35 hours in his lifetime waiting for the ketchup to come out. So this is something they have, the ketchup manufacturers have not managed to change the flowability of ketchup. They're just still using it as marketing. And now if we're rheologists and we're thinking about this, we see, this seems like it's something different from just like a very high viscosity fluid, because there seems to be maybe some time-dependent effects. And maybe one of the first things that we would think about is like, oh, maybe this is like thixotropy. I'm sorry, I should point out on the ad here, it has one little blurb that if you zoom in, it says that it takes 5.7 seconds for ketchup to come out. And this is something of an average value. So I just wanted to point that out because we'll be talking about that a little bit later also. So we see this and we think maybe this is time-dependent rheology. Maybe it's thixotropy. But something that was in my title and something that I actually investigated a lot is, what does thixotropy look like for ketchup? And I'm not going to describe this in detail. I'm just going to show it. This is a startup of steady flow curve. We track the stress while just increasing the shear to cause yielding. And we find that there's only a very small amount of stress overshoot, even on ketchup that has been allowed to wait for a very long time. So we can say when we're trying to understand the flow of ketchup in a bottle, we're just not going to consider thixotropy for now. It's something that ketchup experiences, but it's more scientifically interesting rather than practically interesting in this case. Now, ketchup has a couple other impacts that are interesting. Something else you might be familiar with if you eat it a lot is called syneresis, where if you put some ketchup down, it'll have this sort of watery layer, especially in the first bit that you push out. And this is measured industrially by literally putting ketchup within a target, waiting and seeing how it spreads out from there. And this is something that has actually seen some inventive solutions. The reason that this happens is that the water that's naturally in ketchup sort of separates from the gel over time. And so if you have something to mix it, like this is a patented solution, the syneresis negation apparatus is a cap that if you attach this to the end of your bottle and extrude through this, it mixes the ketchup while it comes out. And so you no longer have this problem. But this is something I have yet to see on the market shelves. So this is an unsolved problem within the ketchup industry. One other interesting application of the dispensing of ketchup is the Automato, which is an RC car that someone has to automatically dispense ketchup. So this is not completely automatic. This is someone who actually has a little remote control that is moving the bottle around to put the ketchup onto the burger. And then we can talk, ketchup, I know ketchup in the context of how popular it is in America, but worldwide, tomatoes are produced in nearly every country in actually fairly large quantities. So there are hundreds of millions of metric tons of tomatoes per year that result in a few million tons of ketchup every year. And within America, there are the numbers, it's a bit hard to track down exactly, but there's 10 to 100 billion ounces that are consumed, resulting in 1 to 10 kilograms per capita. So on average, every person has a few kilograms of ketchup. When one ketchup packet is about 9 grams, that means that everyone eats about 100 to 1,000 of these per year, which I think seems like a reasonable number. But also ketchup is so widespread that one study said that 90% of Americans have a ketchup bottle in the fridge. And so this is something that is also partially motivating our study, that any insight we can have to ketchup can potentially impact 97% of Americans. And then whoever else around the world is dealing with ketchup or related salsas or hot sauces or other condiments. And so we started our investigation by doing a natural study of what happens in a ketchup bottle. So this is a regular Heinz squirt bottle that I have with me that I dissected so that we could get a very clear view of what's going on inside. So let's say we deposit a little bit of ketchup on the top corner. And then we can observe what happens here over time. Just under gravity, the ketchup starts to flow. And we can make some like back of the envelope calculations, maybe where we want to get what is an average stress experienced by the ketchup during this process. The ketchup has a force of gravity. It has some characteristic dimension and a density. So maybe this is something like ketchup under a controlled stress experiment of maybe 50 pascals or so. And so it also clearly experiences wall slip. And so this is something we might say is one case of what happens when you have ketchup you're trying to get out of the bottle. And this is probably one of the best case scenarios because everything kind of comes out smoothly, but it does take quite a while. So if we're thinking about the time of 5.7 seconds, we're definitely slower than that because it takes longer than that for the ketchup to even noticeably start flowing. In another case, if we start with a lot more ketchup, we see other effects where the ketchup almost immediately starts falling down, but it ends up leaving a streak that stays even after 10 minutes. And I should also point out that what we're doing is different from what people know as Liquid Glide, which is another product that came out of MIT where people were studying the surface coating of bottles so that they could get all of the ketchup out of a bottle using this, where they have an oil impregnated textured surface like within the bottle. But in this case, for this presentation, we're discussing the ketchup material itself and not really the surface or the surface coating. And another reason we're interested in ketchup is it's a good example of a yield stress fluid. So yield stress fluids are fairly pervasive, along with particulate or fibrous suspensions like ketchup. You see them in other food products. You see them in building materials, in healthcare products, and like dirt and soil and clay in the world around us. And these are all united by having common features of the microstructure, if you look at them closely, where they have particles inside that are able to jam and interact. And these interparticle interactions lead to the time-dependent effects that we see and that we're frustrated by and that we're so interested in studying, like hysteresis, thixotropy, aging, shear banding, wall slip. And ketchup, I already said, experiences some thixotropy that we're mostly ignoring right now, and also aging and wall slip, which we'll be talking about more. And one of the basic ways to understand this is using a Herschel-Bulkley model to model the flow of ketchup. And so this has a yield stress parameter. So below a certain stress, the material will act like a solid, and above this stress, it will start to flow. So it will have a flow curve that looks approximately like this with a plateau region and then flow. And this is in contrast to something like a Newtonian fluid, which will flow under any imposed stress at all, or a shear thinning fluid, which you probably heard of, which will flow, but just with a different slope compared to a Newtonian fluid. And this yield stress parameter itself is very important for understanding and characterizing materials with different applications. And now how we actually make a measurement is when we go into the lab, we go to our rheometer and we will put sample material into a cup or whatever sample holder we have on the rheometer. And then we have, in this case, a vane that we insert into the material. And so this goes in, this rotates, and as it rotates, we will apply a rotation rate, and then we'll measure the resulting torque to get our values. So here, this is a vane that has 4 arms. It rotates, and then it yields some portion of the material, so that you have a radius of the vane, a radius of the cup, and then a radius of the yielded portion of fluid. And then we use certain equations that we've developed for translating the measured torque into material shear stress. Which for this case, what is often used for the vane is a cylindrical stress model. So you just assume that even though this is something with 4 arms, it behaves as if it were a cylinder. And then for translating sorry, my animations are behind. Oh, there we go. It's strange. Okay. Sorry, minor technical glitch. We also convert the rotation angle to strain, where theta is the angle that the vane has rotated, and strain is the material level measure of the displacement. And so for this, we're using an equation that does assume some simplicity of the material, but it's approximately close enough for our case. But now looking more closely at the 4-arm vane, we participated in some studies doing a simulation of what happens when this actually rotates. And this is highlighting where the yield surfaces are on the material, where people might assume that they're circular. If you look at a cross-section, in reality, we find that they have a very lobed-like structure. And this is because if you do careful stress calculations, if you have a 4-arm vane, then you're going to have points of stress singularity at each of these as it rotates concentrically inside the cup. But we found in a previous study that as you increase the number of arms, this does smooth out considerably. And so we introduce a second stress model that takes into account the number of arms. It's a little bit more accurate than something that just assumes everything is a cylinder. We did more studies to see what is the yield surface for vanes with different numbers of arms. And we found that once you get to about 12, it's pretty much circular, like that becomes a decent approximation. And so for our studies of ketchup, we are using a 12-arm vane. And this is something that's actually very important if you're measuring history-sensitive materials, because you want the stress to be uniform. Because if you're applying different stress levels in different parts of the fluid, then you're going to be measuring something that is less accurate, especially if some point has like a very high stress and it causes the material to yield early, then you'll have trouble actually connecting what the yield point is to what the material flow is. But you also want to minimize how much sample you displace when you insert the geometry into the material. So when you do the initial loading, because any sort of displacement due to the structure will cause deformation before you start the measurement. So now back to ketchup. Ketchup is mostly made of tomato concentrate with a little bit of vinegar, sugar, salt, and flavorings. It forms something that is mostly an aqueous solution of pulp. So the main interacting structures inside are just fibrous ketchup networks from the cell walls of the tomatoes that have been sheared and homogenized. And so we take our vane and we measure directly in the ketchup bottle. So this is something that goes beyond simply having a tool that's designed to not displace a lot of material, is we're able to measure without even dispensing into another cup. And this is something that's not exactly new. There are fixtures for standard rheometers where you can mount whatever tool you want. But for our case, being able to measure in the bottle itself is fairly necessary for being able to measure like the pristine microstructure without having to disrupt it at all. And so what we get, going back to our Herschel-Buckley model, we have a flow curve for ketchup here. And we find that the yield stress is about 20 pascals. To give you some context, tomato juice is about 1 pascal, ranch is 2, tomato paste is about 50, mayo is 60, then you have peanut butter, which is much, much higher, and then Oreo cream, which is 10 kilopascals. So ketchup is fairly flowable, but it has some noticeable structure. And you can see it has the characteristic regions. It has this plateau with yield stress, and then it has this flowing region once you get to higher shear rates. And this data was measured for the average of 5 runs. So you can see there's a little bit of error here around the yield stress. But this is the model fit. So now we want to understand the time-dependent properties. So what happens if you start from rest? And so to do this, we do creep experiments. So how these work is you start with a pre-shear, a preconditioning step to reset the material to the same initial starting position for each of the tests that you do. And then you apply a constant stress, and this is what is the creep experiment. And we do this for different stresses relative to the level of the yield stress. So the results of the creep show that initially you have an inertial response. This is just part of how the test works. Then you reach a plateau region. Here, this is for stresses that are below the yield stress. There's creep. This is Andrade creep, where you just have a very shallow time dependence where the material is very slowly creeping inside. And then maybe it looks like we have hints of some flow after you get a couple minutes through the test. And we can keep in mind the 5.7 seconds that we were thinking about earlier. Clearly, if you apply too little stress, this would be equivalent to having only a very small amount of ketchup in the bottle that's flowing under gravity. Then you are missing the 5.7 second mark. Now, if we apply higher level stresses, so these are stresses that are well above the yield stress, then we get flow. And so here, as the stress increases, you see a definite transition from material that acts relatively like a solid to fluid that is flowing readily. And this has a slope of 1 up at the top here. That is just basically pure displacement. There's no inertia, it's just material flow. And then we can see there also seems to be a little bit of a transition region here, so we can mark a critical rotation angle. Right, so this is tracking what is the angle of rotation as you apply the constant stress. And this is a function of time. So we have the angle here, and then we have the strain here. I mark both of those because the angle is something that we know for certain. We know where the vane is, we know how much it has rotated, but the strain is something that is a little bit dependent on how much of the material has yielded. It's slightly less of a precise value, so I just mark both of those. And now if we measure in the middle, this is where the most interesting things happen. And so here we see we very neatly complete the data between the low and the high cases. So the most interesting thing here is this is called delayed yielding, where material seems like it's relatively stopped, and then all of a sudden it reaches this critical value and then it flows. So overall, what we've seen here is if we follow what is the displacement or strain as a function of time, we get a little bit of inertia, we have a very low level creep, and then in the most exciting case, we have a very sudden rise, which depending on the case, it can have a slope that is much higher than even inertia, but in most cases, it's even higher than just the steady flow state. And this is the part that is where all of the ketchup comes out. Now we can look into this a little bit more detail. Here we want to pinpoint what is happening when, because right now we can just see the curves and everything is kind of like rising. At some point we have this critical strain, critical displacement, which is useful. Now we plot this on a different scale, which is looking at what is the shear rate over time. So again, this is applying a constant stress. And so we can see at the lowest cases, we see the material is slowing down. That's because this is on a log scale thing. This is creeping, so it looks like, oh, maybe eventually, just like a little bit longer, it'll reach the critical value, and maybe the red curve will eventually flow. But it's actually a little bit longer, can end up being like weeks if you're extending this, extrapolating on a log scale, because the material is slowing down. So it's a little bit of a question of how close actually is it here. And so we want to kind of figure out even better how to pinpoint these regions, because on this sort of a plot, you see it does emphasize a little, we see an inflection point here rather than just like kind of a transition of the slope. And so we just want to understand that better. So we have, as part of the study, introduced a new term to help understand this, which we call spurt. And spurt is defined as the second derivative of basically the strain acceleration over the shear, or the shear acceleration over the shear rate. And this is interesting because it looks like it should be an acceleration overall. And there's inertia earlier in the system, which gives the t-squared dependence earlier on. But what we're actually measuring with this term is how fast is the rate of change of the shear acceleration to the shear rate. And so we can write exactly the same thing in a different form, where here we're taking d shear rate dt, which is the top term here, or we can write it using logarithm form. These are all equivalent. And this would have units of rate, given how we've written it. And so if we plot this, what we find out is that it pulls out like very clear, distinct peaks for each of these avalanches. And so this is how we've pinpointed them in time. So here we see something that's like maybe a relatively indistinct increase where there's definitely something happening. Here we see a clear inflection point. And here we see a very well-defined peak that has a maximum, it has a width, it has a time. And you can see also interesting that it shows it clearly for ones that we can see have an inflection point on the other plots, but it even pulls out peaks for the curves that seem like they're just going under like fairly standard transitions to flow. And so we can take this information and we were able to plot what is the central time of the peak of the avalanche for each of these as a function of the yield stress. And so as we approach the yield stress from above, a value of 1 here would be applying exactly the yield stress. We see the time it takes to reach the avalanche increases very sharply, where we would expect this to basically diverge. So it can take longer and longer and longer to reach for the material to start to flow. And so this is again compared to our 5.7 seconds. It's clear if you have enough stress or like equivalently enough ketchup in the bottle, then you're going to yield, or then you're going to like very safely get ketchup to flow within that time scale. If you have less ketchup, then it can take much, much, much longer for the ketchup to flow. So now we can recap what we've learned in the context of some of our tests. So we had 2 cases that we saw before of what happens inside the bottle. So case B here is if you have a lot of ketchup, this is something that has sufficient stress that it's probably able to shear internally. And so that's what's happening here is the ketchup has started to yield. There's a little bit of delayed yielding and then it falls down. So we have more or less understood that rheologically. But the first case, where the material slides down the sidewalls, this is something we haven't discussed at all, because one of the reasons we use vanes for measurement is avoiding slip entirely. But we will now want to understand slip, so we have to do something a little bit different. So to do this, we went back to the lab, and the normal rule of using a vane is you want to insert it completely into the material. But we decided to break the rules of measurement and actually measure with the vane at different heights, either at the surface or a little bit above. And we measured the same flow curve we had before. Here, this is in machine units. This is in rotation rate and torque rather than stress and shear rate, because we're still figuring out what's going on. And we have the equations that we had before for how do we understand what is the torque as a function of everything else. And from these equations, we could work out what are likely conversion factors if we wanted to understand what the material properties are of a material that we're measuring with the vane not completely submerged. So we made two conversion factors. These just use the ratio of what is the torque that you would expect in the basic case, or what is the torque on a vane that is incompletely submerged. That is something that has this partial submersion compared to something that has full submersion. And so, for example, if you have a vane that is under or at the surface, then there's no change here. If you have something that's a little bit above, then this value starts to decrease. So the shift factors that we would have would look like this, where as long as it's below the surface, it's about 1. And then as it goes down, then you see less and less torque just as the vane comes out of the surface. And it turns out that this actually was able to, without any modification, collapse all of our data onto itself. And so this is a very interesting finding because this means that we're measuring the same data no matter how deep the vane is in the material. And what this means actually is that if you want to see what's happening, ketchup is very opaque. So if you put a vane all the way inside, you can only kind of see the surface move. But if you're comfortable knowing that no matter what depth the vane is, you're still measuring the same thing, that means that we can insert a vane halfway through and look at the visible surface. And that would be equivalent for this material for being able to actually see a cross-section within the other case. And so this is something that we did. We have a cup of ketchup here. This is in a smooth-walled 3D printed container, and I took a little stamp to put a target pattern on here so we can see much more easily what is happening when it deforms. And so again, we have the radius of the vane, and then as the vane rotates, it will cause material to yield out to a yield radius, Ry. And we can calculate like what we think this should be based on conservation of angular momentum. We have a torque that's exerted on the vane that is the yield stress times the yield stress times the circumference at the yield radius. That's kind of by definition at the yield radius, the stress is going to be the yield stress. And at the vane, the stress is going to be the measured stress. And so equating this, we know that the yield radius should scale with the stress to the 1/2 power. So as you increase the torque, and this is also equal to what would be the torque over the yield torque. So if we have the torque if we have these equal to 1 and the vane is rotating, you can see that the target remains undisturbed and the vane is just in place. As we increase this value, we start to get some of the material displaced around the edge. And then we also see some slip around the outer wall. This is where these lines, instead of being straight, they start to bend. And then as we increase this even more, these same effects occur, but even more dramatically, where here slip is so large that the target on the outer surface is starting to become destroyed. And this is in contrast to other measurements we did of mayonnaise. So it turns out ketchup is America's 3rd most popular condiment, and mayonnaise is 1st. It's about twice as popular. But mayonnaise is actually extremely difficult to measure, not because of thixotropy or anything, but because it shear bands. And this has been studied before in careful MRI studies of emulsion-like structures. So the microstructure of mayonnaise is that it has oil and water emulsions, and these sorts of materials, it's very easy for them to form depletion zones within the material. This forms like essentially internal structure, so the material slips on itself. And even if you're using a measurement tool like a vane, it's not going to be able to grip the material. And so here, even if our vane is rotating very, very fast, the entire target remains undisturbed because the material is just slipping on itself right at the vane radius. So it's essentially impossible to measure. But back to ketchup, which is much more nicely measurable. Here we can plot what is the radius, the yield radius over the vane radius as a function of the applied stress. And we find when we have slip, it falls something that's below what we would have wanted with the 1/2 power law. And if we do the same test in a cup that then has texture, then we find it obeys what we would have expected. So this kind of confirms that when the material slips, not all the energy is going into shearing the material. There's a lot that's lost to just the material sliding along one of the surface. And so this protocol also overall is really great as a way to view material deformation when the materials aren't transparent. Because not everyone can do something like an MRI study to actually see inside, but everyone can kind of see the surface of the fluid that they're looking at. But in this case, slip is dependent on the interaction of the ketchup with the surface that it's on. So rather than using this 3D printed material, we set up another test to measure slip on the ketchup bottle itself. And so for this test, the idea is you have ketchup sliding down an inclined plane under the force of gravity. And so with the other half of the ketchup bottle, I mounted it on an angled holder. And so you add ketchup, you watch it slide down, and then you can measure what is the sliding velocity, which is the key parameter as a function of what is the mass, what is the angle, which describe what is the stress that's going to be applied. So we did this, in this particular case, it leaves a large track of fluid as it goes down. So this is more like case B that we were looking at before. And so we did this for several different cases with different amounts of fluid and different measurement angles. And so the equations that we're working with here is we have a wall shear stress on the force of gravity divided by the area of contact that it has. The top image here is a side view, the bottom image is a top view. And then we can approximate what is V over the area of contact as something like an effective height and use that to develop an equation. So rho GH sine theta describes what is going to be the approximate wall shear stress as the ketchup falls. And so we measured what is the sliding velocity using videos and my apparatus. I have the sliding velocity and then I have what would be the time for the ketchup to fall, knowing that the bottle is 100 millimeters tall for the bottle that I have. So in general, if you have a lot of ketchup or a high angle, this results in a high shear stress. And so you always have cases where you leave residue as the ketchup falls. You get to a lower level that's close to the bounds of the yield stress, where you start to have cases where some ketchup yields and some of it doesn't. Where you leave just like, rather than like a very thick layer of ketchup behind, you leave maybe just like a few spots of residue or something. And this is probably just because of the surface structure of the bottle, that it might have some imperfections or some little spots. And then the most interesting case is if you have the shear stress that's low enough, then you actually have ketchup that flows that leaves no residue. And so this is something that in the ideal case, you would be able to use this and get all of the ketchup out of the bottle without any residue. But the very sad point is these only occur very, very slowly, which means that you would have to wait minutes or hours for the ketchup to come out. And so we can understand this also using a slip law. This is the wall shear stress is equal to a critical stress plus a factor times the slip velocity to a power. This you can see is very similar in form to what we know as the Herschel-Bulkley model. This is a common slip law for yield stress fluids. And we find this fits well to our data with parameters of a fairly low critical stress. And this is actually the thing that something like LiquiGlide would fix. So while we want to study the material itself, LiquiGlide would fix the slip properties of the vessel so that anything could slide with a much lower barrier. Maybe get rid of the critical sliding entirely. And you might also see this equation in different forms, depending what literature you read. If we rearrange it, this is the form that I showed you, we can just bring one term to the other side. And this is another form that's very, very common, where you just have the difference between the critical and the observed stress to a power is proportional to the slip velocity. Okay, so now this is our understanding of slip. We have it modeled and we can see what's going on. Now we want to bring things back full circle to what's going on inside the bottle. So here we did some more studies of what happens with a ketchup bottle that has been preloaded with either a large or a small amount of ketchup. And when we're pouring ketchup, that means that we have our bottle and we're just holding it still. So either holding it still straight or holding it still at an angle and just observing how long it takes ketchup to get from the top and the back all the way to coming out. And so for context, this is the high level of ketchup is about 1/3 of the bottle full, and the low level is about 10% full. And so we add it, you can see what happens here is the mass is there's definitely an influence of having the ketchup bottle at an angle here. The ketchup will come out much faster. If you have it just straight up, it might not come out at all. So it helps to have the ketchup bottle angled rather than straight. That has an influence of changing what is the angle here so that the ketchup can actually slide down. But you can think that what most people actually do is they shake the bottle. And so we added these experiment cases to what we were studying. So we did 2 different cases of this. One is tapping, where you move the ketchup bottle on axis and you just at like a very small amplitude, and you can either tap it onto a surface or you can just shake it. And according to our data, that didn't make much of a difference. So a small amplitude, a frequency of 4 Hertz, or you can shake it, which is a much more dramatic shaking of the bottle, but at a slightly lower frequency. And so here, if we start with a higher initial mass, you can see that the ketchup starts flowing quite a bit faster for both of these cases. And if we start with a lower mass, it also starts flowing faster. But for all of these cases, we found that we reach something that we call a residue threshold, where no matter how you shake or how you pour or what angle or what frequency you use, you're going to always have just a little bit of residue left inside the bottle. So we collected all of our data together to see, according to what protocol you use, you will always leave more residue, statistically more residue, if you simply pour rather than if you shake or you tap. So it is definitely better to get the ketchup out if you do shake it, rather than what they showed in the commercials where you just kind of hold the bottle. And the time it takes the first bit of ketchup to come out is also significantly faster, even more dramatically so, when you shake and when you tap, rather than when you just wait. And then if you remember that a ketchup packet is about 9 grams of ketchup, that means that we're actually leaving a lot of residue in the bottle when we try to do this. And this is in the context of having a container that has about 400 grams total, which would be 44 packets. So we're leaving as much as 5% of the ketchup still in the bottle. So now we can kind of bring this together to more or less conclude our findings of what's happening here. So we can watch this video again just to see what's happening. So this is, again, clearly dominated by wall slip. And that's basically all of what's going on here, is there's little enough ketchup that there's no internal shear, except maybe a little bit at the end here. But then it's just sliding and then it's coming free without leaving basically any residue. So this is great because it leaves the bottle clean, but it's bad because it takes a lot of time. And then in the second case, we already discussed, this is mostly dominated by creep and avalanching flow because the force due to gravity is larger because we are starting with more ketchup here. So in conclusion, I have presented you with the data that can support the knowledge to help the 97% of Americans with a ketchup bottle save time and food, where you can shake rather than just pour. I've given you information that you can use when you're in the kitchen to just look at what's happening in your ketchup bottle or other condiments and see if they behave the same or differently. There are tools for manufacturers to get information about maybe thinking about having to deal with the residue that's so often left in ketchup bottles. But beyond ketchup itself, we have more wide-ranging impacts from the tools that I've discussed and the measurements we've made, where yield stress, creep, and avalanching are present in a vast array of fluids of different scales and different types. For any material that goes from a non-flowing to a flowing state, these sorts of tools are useful. And specifically, we have equations to measure avalanching timescales, which can save lives, especially if you apply these to actual avalanches. And we have tools that allow you to directly view wall slip and material deformation, which can allow new data collection for a wide variety of materials. And so one final suggestion from our study is if you look at the ketchup bottle, if you look at it very closely at the outline, you see that a lot of where residue comes from is it actually gets trapped at the walls. And so a simple redesign of the bottle could be something that could actually save, rather than having to have any special coating, if you just eliminate these sharp corners, you could save those extra few ketchup packets worth of ketchup that get stuck inside. And then one last recognition. So just in light of the name of this webinar series, MIT is definitely a fan of Douglas Adams and the Hitchhiker's Guide. So there was a hack when he passed away saying, "So long and thanks for all of the wit." Where they had this and then they had a towel, which if you're familiar with the series, you understand why that is important.
You always need a towel.
Yes. Then you look prepared.
Thank you.
Thank you.
I didn't know about the hacking at MIT. Nice.
Yeah.
That was a very great talk, Crystal. Thank you so much. Questions? Yeah, people, come on. I have lots of curiosities and questions myself. For example, I mean, curiosity, I didn't know that actually mayonnaise was the first condiment in the US because I don't know there at MIT, but here in New York, I always have to ask for mayonnaise when I go out. They always just put ketchup on the table.
Yeah, I think that's something that's popular in the home. I think if you go to a restaurant, you're gonna find salt, pepper, and ketchup usually.
Yeah, never
So
mayonnaise.
that's interesting. Yeah, but this is the actual chart of what is. So mayonnaise is number 1, ranch is 2, and ketchup is 3.
Oh yeah, as an Italian, I've seen ranch where it shouldn't be.
I'm sorry.
Marjorie, please.
Hi. Yes, so I'm actually logging in from Sweden at the moment.
Nice.
Yeah, so this is my first time at this webinar, and I'm actually not a rheology person per se, even though I've tinkered a bit, very little bit, but I'm a food scientist. So, I mean, this is one of the first examples that you get taught of when you go through fluid mechanics when doing your bachelor. It's like, yes. Ketchup is interesting. But my question is about, well, I mean, I saw that you tested it on plastic on the plastic container, but what happens in a glass bottle? Because the surface is going to be different as well. So I'm just curious if you ever tested even just like slightly or like once, what happens in a glass bottle? How are the effects that you saw different in any way?
Yeah, no, that's a really interesting question because there are surface effects from having glass, and glass is also a lot more rigid.
Yeah.
So plastic versus glass, there's actually a lot of literature about what different slip laws that you're going to get because one has attractive interactions with generally suspended materials, and one might be more repulsive.
Yeah.
I did not actually test on glass bottles, but I would expect that it would come out a little bit smoother.
All right.
But actually, one of the main advantages of using plastic is then you can have the deformable container so that you can actually squirt rather than having to depend on slip, which I think actually saves a lot. Because if you have something stuck in a rigid container, then it's kind of stuck.
Yeah, it's a bit harder. Absolutely. But I mean, for food preservation matters, the glass is better. So,
And the environment too.
yeah.
Yeah.
Which is curious because I believe that they've been using glass for a long time before using plastic. I mean, if you even the advertising you showed the first video you showed, it was a glass bottle, I think.
Yeah.
And every time you look at these other brands that try to make some more vintage ketchup, they always try to use glass bottles, which,
Yeah.
as you said, I would also expect to have a bit more wall slip. Maybe I'm wrong, but.
Yeah, so I would think that the glass would be better. But actually, if you think about it from like a manufacturing economics state, I think what you're able to do with plastic is you can make it more of a square container. So you can fit
Yeah.
more bottles in an area than you could if you just have a circular cross section
Is
bottle.
it also because it has the little nozzle most of the times, and you can only squeeze it out with a deformable container, right?
I think that's an advantage, but I think if they were able to mold glass very easily into a squarish container, then they might do that instead.
Yeah. But I mean, then wouldn't you have like more residue in all of these corners versus like a smooth thing?
Yeah, that's the point. You wanna avoid the corners. And so plastic is just much more amenable to different design sizes or like the peculiarities of little design parts.
Oh, but usually the glass bottles don't have the corners close to the neck.
Yeah, that's a longer.
Yeah, it usually goes just straight out. Oh, interesting. Emilia, please.
Hello, can you hear me? Yeah.
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 Okay, well, it was really cool. Yeah, it was really cool. Thank you very much. I have actually many questions, but I think I'm gonna try to not give you an avalanche of questions. But first, this geometry is super interesting. I'm kind of like, I just started my PhD, so I'm kind of new in rheology and you have like this vane geometry, and indeed, wall slip is impacting a lot of yield stress fluids, or maybe a lot of fluids, right? I'm working with some yield stress fluid, and I have this wall slip problem. So I have two questions regarding this geometry. Well, first of all, I just naturally would imagine that you have this paddles in this geometry, and you will have volume that gets trapped, right? So how do you deal with that? Is it not a problem in like studying the flow?
You mean it's like getting material stuck into like the little interstitial spots here? And you mean
Exactly. Yeah,
like during
especially
measurement
in
or
this 12 paddle geometry. Yeah, material that it's just not really flowing, not moving.
yeah, so part of the point of using a vane is that you expect that the material doesn't flow. So here, the approximation that you make when you say everything should be a cylinder is that you say that, like, if you have this forearm vane, you imagine that everything within like a cylinder equal to the radius of the vane is not moving. So it's as if you're moving a cylinder. And what you're
Mhm.
measuring, this avoids slip because rather than having like a smooth, like actual metal cylinder that the material can slide on, the material is shearing against itself right here. So you get shear deformation. So you actually do want material to be trapped inside here. So it's not moving inside the radius of the vane, but then it is shearing on the outside. So you do want that. You don't want bubbles. So that's something you could choose something maybe like a 6-arm vane if you have like a lot of bubbles or aggregates or something, so that you can insert this and have it very smoothly filled with material, but you do want the material to not be sliding or not be
Okay.
shifting inside.
Okay. All right. So then, do you think that for this kind of vane geometry, there's like a range of viscosities or yield stress that you would have to like limit so you can use this type of geometry?
I think the biggest challenge would be if there are some sort of aggregates, then you definitely want the spacing to be large enough that nothing gets trapped. But like here you can see the example where we have the vein inserted into ketchup. It's very smoothly like filled these holes. If I try to insert into something, this has a yield stress of about 20 pascals. If I insert into something that has a yield stress of about 100 pascals, I start having to maybe use a spatula or something to help make sure it gets filled in.
Yeah.
But if you have a challenge like that, you can also take the same thing. This is a 3D printed design that I have shared online. If someone wants to make their own, you can just scale it up, which can also handle something like aggregates or filling the small void spaces. Yeah, but
Okay.
you can kind of make your choice. If you can kind of like insert a knife into your material and see like how far away does material displace, you can kind of make a judgment of what seems like the best choice.
Okay. Thanks. And just one more question. For the creep tests, you chose the stress based on that yield stress, kind of like close values that are close. So
Yeah.
yeah. Okay. Yeah, I think that, well, I just have one little question, which is just for a fun thing. It's why tomato ketchup? Why do you call it tomato ketchup? Is there ketchup that's not tomato?
Yes. Actually, I found that out when I went to Mexico once and I asked for ketchup and they brought cherry ketchup,
Oh wow.
which looks very similar. Also, banana ketchup is very popular in Asia. It's something that they had apparently developed when tomatoes were harder to source then. They actually color it red also, so it can be a little bit in disguise. But
Oh,
I think
okay.
it's only in America that I've heard that ketchup means tomato ketchup. In other places, ketchup is just the name of like a type of sauce. Like you would call something jam or jelly, you'd call it a ketchup.
All right. Okay, cool. Well, thank you very much.
Thank you.
Shubhangi, please.
Yeah, so really nice talk. Am I audible to everyone?
Yes.
Yeah, okay. Yeah, so it was a really nice talk, very interesting work. So, like my most of my questions actually got answered in your previous answer. So I had a little thing. Uh, so you mentioned that uh, uh, if you take a little amount of ketchup, it easily slides down, but there is no residue left behind. But if you take a lot of amount of ketchup, it slides down quickly, but there is residue left behind. Okay. So, like, my first question is that what are your thoughts that why does this happen? So, my intuition is this probably happens because of the weight. So, there you have a lot of amount of ketchup, so it's exerting more weight, so it's able to shear it more. That's why. And my other question is that there is a phenomena of residual stresses that has been observed in thixotropic materials specifically. So, like, uh, does it have to something to do with that, or is it something else? So, your thoughts on that?
Oh, residual stresses are really, really interesting. I think they're present in every yield stress fluid. So they're definitely present here, although I didn't measure them in particular. Usually residual stresses are about stresses that are retained by the material up to about 10 to 20% of the yield stress. So in this case, that would be about 2 to 4 pascals.
Okay.
So I don't think those are playing a role in the sort of residue that's left when the material slides. I think it's exactly what you said, that if you have enough stress, then the material is sliding, but it is also under enough shear stress that it is above the internal yield stress and it is able to just shear. So rather than like sliding purely, it is sliding on like a very thin layer of additional ketchup. So it's just something that
Okay.
has exceeded that stress. And it's only in like this very narrow region where you are above the critical slip stress, which is set by the plastic bottle material. You're between that and you're between the yield stress, and there it's able to slide, but it's under little enough stress that it's just above one critical stress, but it's still below the other one, so it's able to slide without internal shearing. So I guess that this
Oh,
is
okay.
like
I see.
almost
Okay, I
similar to
see.
like
This is
adhesion
the
versus
point.
cohesion. It's only
Oh,
interacting with the material, but it's able to slide as if it were a solid.
okay. Okay, I see. I see the point. Okay. Okay. Thank you. Thank you. Great talk.
Thank you.
We then have a couple of questions in the chat. I'm going to read them out just to also have them in the recording. So Sashi says, thanks for the interesting talk. And could you please play again your ketchup sliding at an angled video? I loved it. And can you tell us, does the ketchup dance or move in different ways? I mean, local stress weight distribution as it is sliding down when you change parameters such as volume and angle?
I didn't quite local stress and weight distribution. Um, I think you can tell from my video that we definitely have some initial, I'll play it again from here. We definitely have some initial inertia as the material is put down, and that is definitely affected by the amount of material, especially if we have a lot of ketchup. You could see this little bit kind of like it kind of flips around there. But then very quickly, like by this point, it has reached a steady sliding velocity. And that's the point where we start taking the data. I don't have any measurements of the local weight distribution, but I would assume that it's fairly uniform, just basically based on what is the height of the ketchup in local areas. But we're kind of making, like, obviously the geometry is not controlled as this slides down. So we're more or less making assumptions that it's sliding just as a solid object. Like the math that I had worked out assumes that it has an average height, it has an average area, and then otherwise it's treated more or less like one solid object. Although it could be factors like that that lead to some of the slight noise in the data as it goes down. Or those could be effects of the ketchup itself being inhomogeneous.
Nice. And another couple of questions also from the chat. So, what type of dye did you use to mark the surface pre-tests? And were all these tests performed at room temperature?
Yeah. Oh yeah, that's a good question because people usually use ketchup when it's colder if they keep it in the fridge. I did everything at room temperature just because of all of the different devices I was using. It was much easier to keep it all at one constant temperature rather than changing it back and forth. I think by dye, if you mean
Yeah.
the surface marking, what I used graphite flakes that I put down. So it's just individual particles, and this is why as the vane rotates and it shears them, they kind of like become invisible because they have been mixed in with the material. So it's just graphite that you would get for like lubricating car wheels or something.
All right. As you're on this slide, I also had a question about these vane experiments. Do you observe any sort of Weissenberg effect? Does the ketchup try to climb the rod when it's fully submerged, or something? I don't know, because I see here some ketchup that is like above the volume line.
Yeah. Oh yeah. So that specifically happens. Oh no, I lost my ability to have a pointer. There we go. This happens because actually to insert the vane, I insert it a little bit extra and then I come back up so that this surface is flat around here. Otherwise, it would be
Sure.
displaced down just a little bit. We don't see anything like rod climbing with
Okay.
ketchup. I've tested other materials like toothpaste or anything that has a lot more elasticity, definitely has very distinct climbing. Yeah.
And when you did your vane experiments with inside the ketchup bottle, do you think that the shape of the container itself has an impact, or
Um,
yeah,
yeah, I think certainly it does have an impact. You can also see it's not circular.
yeah,
Um,
that's why.
But even more trouble than that is it's flexible, which means that if we're rotating the vane at a high enough rate, then we can be sure that the actual dimensions of the vessel are going to be changing very slightly. So for our case, uh, I had measured in the ketchup bottle, I had also measured in a standard geometry, and I found what is an effective radius that makes the two measurements the same. And that effective radius is basically what is the smaller width of the bottle here, because it's kind of like rectangular. And so this is acting as if it's shearing just like a circle. It's mostly confined by the small dimension, and then the big dimension is just kind of like holding additional ketchup.
Great. And one last final question for me, at least. When you did your measurements of how long does the ketchup mm, takes to get out of the bottle, depending on if you shake it, if you wait, or if you put it straight, vertical or inclined, what's exactly the procedure you followed? Yeah, here.
Yeah, so these tests were done manually.
Mm-hmm.
So the procedure was preloading ketchup into the bottle and then making sure it's on the back side of the bottle. So it's
So
always in the
it's
same location.
okay, so
Yeah.
just a small amount of ketchup.
Yeah, and so it would be
Okay.
the weight that I had listed, which is either
Okay,
about a
perfect.
third
Okay.
full or about 10% full.
Okay.
That I measured with a scale just to make sure it was always like approximately the same initial conditions. Because if you have this thing full of ketchup, then the ketchup's just going to come out, and that's not interesting to study. So these were the cases of like, oh, there's like some left, or like, oh, there's just a little bit. How do you get it out?
And do you think that the fact that it's harder for the ketchup to get out when it's vertical, when you hold it vertically, is it also due to the fact that, you need air to go back in while the ketchup is getting out?
I think in these cases, so it's actually kind of like stuck to the top surface here. Or when
Okay.
it's vertical, I think yeah, it has some like suction force that it needs to fall down from here compared to if this is at an angle, then the ketchup can just slide down. This
Yeah.
becomes an angled surface rather than something that it has to like the ketchup has to separate from itself in this case. Here it just has to slide. Yeah, so it's kind of changing how it's able to move. Exactly.
Great. Do we have other questions? No more questions in the chat. Um, okay,
Well,
well,
I had some question, but I think that it's already a very long video. Like how did you create your geometry? How did you find out exactly this shape? Was it like a work that you have done, or was it someone else's work? Because to find I don't know if you can go back to your vein. Yeah, the one on the right. Like this geometry is not something that I've seen before, I think. How did you come up with that?
Yeah, so I published a paper with that
Sorry,
before.
there are people talking. Sorry,
Actually, this is the main paper that I published with that. This was another work that I was part of where we did simulations. But this was the sort of like full optimization where we have, besides vanes with 12 arms, we have 4, 8, 12, and 24 arms that we kind of went through. How do you optimize? This is numerical optimization for how do you get fill the smallest volume so you have the sparsest structure you can make, but have like a large number of contact points. So it's something we went into a lot of detail there to
Okay,
make
I'm
like
gonna
what
read
is
that paper.
yeah, what are optimized tools for history sensitive materials where you want to prevent slip. So it's kind of like a co-optimization of 4 different parameters.
Okay, thank you. I think that there is a question, Christopher. Go
Yeah,
ahead.
Christopher, please.
Yeah, I have a question. Was this tested with another brand? Because I'm aware that the tomato ketchup has different composition. So I'm just curious if the composition has effects on its thixotropic ability.
That's a great question. I did not test on another brand. There's definitely a lot of dependence on if the amount of tomato products in the ketchup changes. That apparently has an exponential effect on the yield stress. So if a company has just a very slightly different process, then they could have very different behaving ketchup. I think, or the overall behavior should be different. It would just be more of like the magnitudes of different portions, like what is the yield stress, what is the critical displacement at which it like suddenly avalanches, or like how much syneresis does it have? All these things would probably not become absent, but they would just change in magnitude for different brands.
Oh, I see.
I tested mustard and I found similar results.
All right, thank you. I mean, even just a minute change can actually change a lot of things, and that's very interesting.
Yeah, it would be cool. Like one major thing that could change if you had a different material that had much more thixotropy, then that could probably change the nature of things. Because right now things are dominated by creep, but if thixotropy became the dominant factor, then that would change a lot.
All right, thank you.
Thank you. Okay. I guess I can stop here the recording.
Yeah, thank you very much.